Hello everyone. So today we'll work on the flip sim, flip solver, and another type of sourcing for the flip. I baked a few things. This is the Symbiote VDB, which is quite fast to read now because I saved it as a sequence. It's a VDB surface volume, and we prepared our source, and I also baked the quad mesh deformed by the wrinkled skin simulated by the FEM solver. So you can see the preview here. It looks alright. We have some interesting wrinkling happening there. We have some compression, some elongation of the arms, and we have some loose movement in the tail, some inflating bubbles, exactly what we wanted and what we worked really hard to achieve. So what's interesting is this left arm, which is kind of twisting, and it creates another set of wrinkles. So it looks cool. Let's instead of this guy use our quad mesh wrinkled by the FEM solver. So we will actually use this. What I did here, I just applied the color. Basically, this is going to be the render mesh, so I'm going to make a null here. And we'll use it afterwards. So out symbiote body render, and I'm using this modified. So basically, yeah, let's do this operation here. I'm going to duplicate it, but in this one, I'm going to just apply another. Maybe let's do it like this, so I don't duplicate any nodes. So we have the color applied here, so it's a gray color. What I did here, I applied an attribute blur of one iteration. There's a slight change here, and I calculated normals. So now our wrinkles get proper normals here. We can increase the iterations to 2, and yeah, and that's cool. And now time warp. So I saved the a newer VDB considering the wrinkles. So you can see that there's wrinkles included in this VDB. We'll use it for collisions and other stuff, but we'll have to readjust some of these parameters, the curvature parameters and the emission parameters, because we changed from this mesh to this mesh, which is the wrinkled mesh. So there's a slight change of geometry and there's more detail, and because it's a subdivided mesh. If you look at the detail here, you have 4 times more vertices than the previous mesh. So yeah, we'll readjust some parameters here. So this was the normal selection, emit, emission blur, maybe, yeah, the emit parameter was this guy. And then you have, yeah, we created a viscosity attribute and a CD attribute, but we have some weird mixing here happening, so let's remove the noise for now. All right, so this is just the convexity of these, the cavities of the mesh. So yeah, the cavities will be multiplied by that normal mask, which is called emit, and our curl noise. So let's readjust some of these things. Let's go back to the ramps here and see what we can do. Oh yeah, the viscosity, I'm gonna touch it. The emission here, yeah, and the curvature. Yeah, these 2 parameters are not very useful, but yeah, the noise is here. If we invert this guy, we'll have something like this. We may probably, yeah, let's blur this and see what happens. So this we'll call emission magic. Yeah, so let's use this for emission for now. And as you can see, it's emitting stuff from the concavity. So those areas that are kind of curved, not the crevices and all that geometry like that is in between the bubbles. So we'll scatter some points here. It will probably be too much, but we'll be able to decrease that. convert to VDB. So this was the first workflow that we used, and yeah, we'll change that probably. So we'll use another method. So we'll modify this setup just a little. Here we'll just increase the resolution of this volume. All right, so we'll omit these two nodes because I don't want to do two conversions again. So I'll make a point from volume. The goal here is to have a parameter which is based on a cubic formula. The point separation is a cubic formula because this, every time you increase this parameter, like when you decrease the parameter, it's all calculated at the power of 3 because you have 3 axes inside the volume. So basically, yeah, the points from volume will correspond to the resolution of our flip sim. So let's set it to 0002, for example. Choose dense grid here and see what happens. So now we have this kind of a point cloud, and we don't need these two because they're going to be useless. And yeah, the points from volume will be enough for emission. And we'll probably have to, yeah, because we'll transfer the. You see that we have some velocities in the scatter node here, and it's going to get a little bit heavier here. So we'll have to bake. I think I'll bake this VDB from particle fluid before doing anything. So yeah, the points from volume, we'll add some randomization to this volume. So we'll have random particles, randomized particles in space, and yeah, we will have this kind of a particle source coming from a VDB from particle fluid, and only because there's a parameter called point separation here, which will bind to the flip simulation. So now our points have velocities transferred from the scatter, but I think I'll just be baking, I'm going to copy this guy right here, and in the geocached here, geocached symbiote VDB, I'll name it flip source. Flip source. And I'll save it. I'll come back when it's done. So basically I baked the flip source, which is the volume. It reads really fast, and the points from volume generated from that volume with the velocity and with the viscosity. So let's check the viscosity also. And if you remember correctly, we had the viscosity set to something like 3 to 7, I think. Yeah, 3 to 7. And you can see that there's variation there. So we have variable viscosity emission. Let's jump into a dot network now, because we have all the necessary ingredients to make it work. We have the source, we have the collider. Let's connect the source to the first input of the dot network. Call this dot flip or sim flip. Let's make it sim flip. And let's build our flip network. Flip solver, flip object. I'll just click Shift S just to change the lines into a more curved ones. And let's calculate the bounding box. What I'll do here is take, for example, this time warp, and I'll make a time shift afterwards. Delete channels just so we can set the frame 300, and we'll duplicate it, set frame 1, merge these two together, and we'll have two geometries. And yeah, let's make a bound node here, and we'll have a bounding box now. Let's make a null and call it out flip bounds. So now I'll set this to file, and let's type it in of input path dots input 0. Yeah, file, yeah, we'll just copy it, particle field, and put this. Yeah, because file requires an actual file sequence. So yeah, I'll put particle field here, and we'll set the resolution to 0002. Copy this parameter, go back into the points from volume. This is why I set it to 0002, because I knew that the resolution would be this, and I already baked it, so it's fine. But we'll link up these two particle separations, so they're related. And what else? We have this, and we want to reference our, in the flip solver here, we'll reference the bounding size, the box size. So the expression here, we want to reference that bounding box that we just created. So we'll be using the bbox expression. We'll type in 2 dots / 2 dots / out flip bounds, and we'll use the type dx size, because we want to take the x size. It's a weird expression, but you'll see that it works. So now we have the x size. I copied this thing, paste it 2 times, but instead of the x size here, I'll put y size and z size. Yeah. Now we have the size of the bounding box that is referenced, but the center is off, so for the center we'll use centroid. Let's copy the bbox first, and we'll just replace it by centroid. And instead of dx size, we'll use dx. Copy it, paste it 2 times, z, and in the y we'll put y, and the centroid is properly set here. In order to have some headroom and some space around this box and make it a little bit bigger, we'll go back to the bound, and we'll add some padding to this. A meter of padding. Let's see what happens here. It's too much, so yeah, maybe. Let's do a 0, 2, 0, 2, 0, 2 everywhere. Yeah, let's keep it like this. So if our creature moves or just goes a little bit further, crawls a little bit further, the bounding box will adapt. So this is a good way of keeping stuff procedural. Why I did this time shift on the first frame and the second one on the last frame is to just cover the whole area of the movement of our creature. So I merged them together. The bounding box, the resulting bounding box will contain both of them. So this is the whole path of movement. So let's go back to our flip sim, and we'll start adding some colliders here. Yeah, let's do some gravity first. Gravity for force here by default. A static solver and 2 static objects. I'll add 1 first and then maybe a merge. Let's make another merge here. Add it here somewhere. Before or after the gravity doesn't really matter in this case. So yeah, left input affects right input in a collide relationship. So this one will be called call symbiote. And we already have the collider, so I'll put it in the second. Yeah, in the second input. And I'm not gonna put anything here in the sop path. I'll ignore this completely, but use deforming geometry in the reevaluate sops to interpolate geometry. So we'll just set these guys to 0, like I don't want any bounce. Friction to 1. And in the collision tab, we'll use the volume collisions. Instead of the mode or ray intersect, we'll use the volume sample. And by size, we know that the resolution of our collider is 0002. It's not that relevant. I don't think it changes much, but yeah, we'll, instead of picking this proxy volume with the picker here, I'll use the op input path. I'll just copy it from the actual flip object. I'll copy this and change it to 1. So now we have a collider. As you can see, we can visualize it and it's there. And it's fast to read, so it's all good. And we need to add another collision. And it's going to be the ground collision. And as for the ground, we didn't prepare anything, actually. So yeah, the ground will be just a flat plane. So I'll reference it. Maybe I'll just, make an object merge here, put it here, teleport it to where we need it to be, connect it here. So yeah, and maybe make a VDB from polygons. VDB from polygons. But we don't have any thickness here, so extrude volume. Or maybe, you know, just to not use all of these points because it's quite complex as geometry, there's a lot of polygons. I'll make a bounding box as a rectangle. I'm pretty sure not many of you use this kind of bounding box, but it's quite useful sometimes when you need a 2D shape describing the bounding box of an object. So it's a rectangle. Instead of having 44,000 polygons, I don't need that. It's too much. We'll have 4 vertices and 1 polygon. So I'll do a poly extrude. And do it in the opposite way, output the back. And we'll have our collider. And we'll remove the extrude volume. Make a VDB from polygons. Make it, yeah, something like this. And yeah, maybe that's a lot of voxels. So I'm not going to use all of this, but let me check how big is the bounding box is ridiculously small. So let me make a box around it, or even, you know, let's import the bounding box. Make an object merge here, push this here, and we'll boolean the bounding box rectangle, this guy, and make it intersection. So yeah, the intersection actually cuts a volume, so we don't need the poly extrude. We may probably make another bound here just to increase. Yeah, something larger like this. Keep the other two the same. 0, 1, 0, 1, 0, 1. Yeah, 0, 3, 0, 3. Let's call it bounds bool. Change this to bounds bool. And we'll have a boolean like this. Increase this guy. So now we have a nice collider here. And we have much less voxels. We had like 49 or I don't know, 70 million voxels previously, but we don't need that much. And we'll use the boolean in the third input and the VDB in the fourth. Let's add the ground collider. We'll uncheck these two and use volume collisions. The volume is in the input 3, and the SOP path is in input 2. So now we have the collisions here. Yeah, that's cool. What else? We have the viscosity to set. So yeah, let's do the viscosity. But first, let me check if it works already. And let's save this as a flip sim setup. This is going to be chapter 10. Now let's press this, see what happens here. So what happens here is we have an emission on the first frame, but we need it to emit constantly, or like every few frames. So this was a particle field, which initially was had a specific amount of particles at the start. What I'm going to do is just uncheck this visualize limits because it just messes up with the zooming in the viewport. Sometimes it's too big. So yeah, just falls down. You see the liquid just falls down along with the body and just collides with the ground and the body, which is great. But there's a lot of things to fix here. I'm going to call this guy flip object, and I'll remove cut this expression and make a volume source and connect it to the fourth input, where the sourcing happens, and we'll use the first context geometry into this object, and instead of source smoke, source flip. Yeah, and we'll remove the kill inside SOP. I don't like this option because it just leaves the shell of emission instead of using the volume. So yeah, let's see what happens here. And nothing happens. We'll just remove this group and use all of them with an asterisk, because it's searching for this specific group. If it doesn't exist, it's not going to source anything. And yeah, now you can see that there's emission happening here. There's a lot of particles being emitted safely because the particle separation is the same on both, on the flip solver and on the emitter. So you see that there's a bunch of particles getting emitted here, and we really don't need that much. So yeah, first thing is first, we'll start adding some viscosity. So in order to add the viscosity, we'll go here and read the viscosity from an attribute. It's called viscosity. We created it earlier. It's sourced right through this volume source into the sim. The sim reads the particle attributes. If it sees the viscosity attribute, it's going to read it and copy it and introduce those newly created particles into the system. And we'll also change the velocity transfer to apex swirly, which is a velocity transfer mode which is more suitable for very viscous particles and liquids. And as you know, you need a lot of substeps for viscosity sometimes, especially when you have really fast-moving colliders. And you see that the liquid doesn't spread that much anymore, and it's quite viscous, but it has variable viscosity, and it emits a lot of particles there. And as you can see, it covers the whole body, which is not desired. We have too much liquid. And I remember one of the comments about Joey was that the symbiote emits so much liquid that in 5 seconds it would have lost the whole body mass in liquid. So yeah, it's correct. We're kind of ignoring the energy conservation laws here by emitting more than we can. So let's go back to the sourcing. Oh yeah, so you can see that we have a. Let me check this, hide other stuff, and let me see if we're displaying any collisions. No, we don't. But yeah, we're here, and you can see that there's variable viscosity happening here. Some particles are less viscous than the other ones, so that's cool. But I'm pretty sure I'll rebake these flip source and flip particle source, because we're going to change some of the parameters. I don't like the emission, basically. So we'll go back here to the emission. We'll flip the first ramp. As far as I remember, we had this ramp controlling the curvature, if it's concavity or convexity. So yeah, let's use this as a mask. And maybe change the curl noise. Yeah, we didn't expose any of those parameters, which is too bad. Let's expose this. Frequency. Third click, third mouse click, or third the wheel click on the frequency. And we'll have the frequency exposed at the bottom here. So in order to introduce more breakup, I'll use higher frequency, faster time, maybe 1. Maybe we'll also use more turbulence to break up the emission more. Yeah. And the roughness decides how rough the noise is. Yeah, that's all right. We can also maybe use the inflation of the bubbles as an additional mask to add to this mask in order to emit during the inflation and stop emitting during the deflation of those bubbles. But we'll see if we do that in the future. So yeah, I'll have to rebake this whole thing. I'll rebake this, and I'll make a let's make a dop import fields just to save the simulation. And in the dop import fields, we drag the flip sim here, and the dop node will be sim flip object, and choose either particles or liquid. And I don't want to, let's say particles, just geometry. And if you want to save the color, you just type in /visualization. Then it's going to import this color. But if you remove it, you will not have it. So yeah, flip object. So yeah, we're done here, and then let's clean up this stuff and save it with the file cache. explicit. I'll paste this path that I created earlier, SimFlip draw or symbiote, let's say. Symbiote. Load from disk. And in the flip sim, maybe we didn't change the mode of display here. It's the speed basically, but it's not properly mapped speed. Maybe 2, 1, 0, 6. Yes, something like this. Yeah, that's cool. That's cool. And yeah, we'll use this as parameters first, but before even saving the simulation, I will just rebake the sources because we changed the curvature and the emission. Now the emission doesn't look anything like this. It was like this. You see how much more area you have here, but now it's like this. So we have to keep in mind that there's less emission here happening. So yeah, I'll save the new emission here, and then I'll launch the simulation, and we'll see each other in the next lesson, where we'll mesh this liquid and see if it even works, because sometimes there's too much liquid emission, and we'll have to fix that. See you in the next one.